Topic 2 focuses on the structure of atoms. And what I want to tell you about is a little bit about the history of atomic structure. We want to look at subatomic particles, how this relates to things called isotopes, what they are, and a few examples of those. And then I want to focus very much on electron configuration, or electron orbits, because this will be one of the keys for understanding chemical bonding, understanding the structure of materials and the properties of not only the elements but the materials that they form. The Greeks had this atomic theory. However, they considered atoms rather like solid billiard balls, solid particles of defined size, but nevertheless one sort of solid mass. Later, we recognize that under some circumstances, then particles that we now call electrons can be emitted from atoms. And I'll show you that in a moment. And so developed what's sometimes called a current bun or a plum pudding model of the atom, where we effectively have a solid billiard ball type particle, but stuck on the surface are these things, electrons, which under certain circumstances may be ejected from the atom. And then, moving on from that, there was a seminal experiment around about 1924 by a New Zealand scientist called Ernest Rutherford, but working in England at the University of Manchester. And he determined, and I'll say more about the experiment in a moment, that an atom was composed of a small, highly positive nucleus surrounded by an awful lot of space. We assume that the space contains the electrons because they were the things that could be ejected from an atom under some circumstances. And this was later developed by Niels Bohr into the model of the atom that I want to present to you, in which we can understand a little bit about the atomic nucleus and that the electrons are not scattered anywhere in the space around the nucleus, but are restricted to certain orbits around that nucleus. Now, our current model of the atom is actually a little bit more sophisticated than that again, and involves something called quantum mechanics, which is able to give much greater detail on the structure of the atom and explain many more phenomena. But I want to stop in this bridging course at the Bohr model of the atom, because that covers a lot of the fundamentals that we need to understand chemistry. But first, a little bit of the experimentation that's associated with some of these discoveries. And one of them was the nature of electrons. And I have a couple of bits of apparatus that I want to show you here. What I'm going to do is generate electrons at this end of this vacuum tube. I need this, I find rather frightening bit of apparatus. There's a lot of bare wires, and I'm never quite sure whether someone's, flicked a switch to kilovolts, that's K-I-L-L-E-R, volts, but we'll see what happens. And what you might be able to see is a Maltese cross on that screen. I'm firing electrons towards you, and we can see that they cast a shadow on the end of the screen, a shadow of an object in its path. Now, if I bring a magnet close, and I've only just managed to get the iron filings off the magnet from this morning, you can see that the electron beam is deflected. So experiments such as this were used as evidence that electrons were negatively charged particles. We can work out from physics that a certain deflection caused by a magnetic field indicates a negative particle. And then another bit of apparatus I want to show you is what's sometimes called a Crookes tube, after the guy that invented it, William Crookes. And in this tube I've got a vacuum so that there's no air molecules to get in the way, and a paddle wheel on some runners, and what I'm doing is firing some electrons from the left-hand side to the right-hand side at the top of the paddle wheel, and it moves down the tube. And if I were to reverse the polarities, I can get the paddle wheel to move in the other direction back to its starting place. So this was used as evidence that electrons were small particles and that they had a mass. We've since reinterpreted the experiment a little bit, but that is sufficient for our purposes. So electrons, small particles with a negative charge. Now, I mentioned that Ernest Rutherford made what turned out to be a startling discovery, that the nucleus of an atom was a small part, a very small part of the total atom. He first put on the map the fact that atoms are not billiard board-like in a sort of solid, even density to their mass, but that there was this very small nucleus. And the experiment that he did is portrayed at the bottom here. He actually took some gold foil, and the advantage with gold foil is that you can actually beat it to a very, very thin sheet, literally only a few atoms thick. And he fired at this gold foil a beam of alpha particles. In the turn of last century, they were fairly recently discovered. It was known that they were charged particles and that they were positively charged particles. Again, experiments associated with magnets and deflection. So he fired this beam of positively charged particles at the gold foil and found that the vast majority of them went straight through the foil. There's a lot of gaps there. Some were deflected through a small angle, and some, and this was a real surprise, were deflected through a very, very large angle. And he wrote in his notebook at the time that it was as if he'd fired a bullet at a piece of tissue paper and it bounced back at him. It was quite unexpected. The interpretation led to our modern thinking of an atom, and that is a small positive nucleus. If we fire positive particles towards, say, this atom, most of them will pass through the gold foil unaffected. Some of them that come close towards a nucleus will be deflected through an angle. There will occasionally be one that comes in a path almost directly on the nucleus, and in that instance it will be deflected through a very large angle. And by looking at the intensity of the number of particles deflected through a large angle compared to the rest, Rutherford could work out the relative size of the nucleus in the atom. Okay, so let's have a look a little bit at those subatomic particles. And there are three subatomic particles which we need to study in order to understand the nature of the atoms: protons, electrons, and neutrons. In the table, I've actually given the actual mass of these subatomic particles. What I want to do is look at their relative mass, because that is easier to show you what I want to explain. And let's say the mass of a proton is 1 unit, 1 atomic mass unit. What we find is the mass of a neutron is pretty much the same. The mass of an electron is very, very small in comparison. It's about 1/2000th of the mass of a proton or a neutron. So I'm going to call it approximately zero. Of course it can't be zero, but very close to it. The other thing I want to look at is the relative charge of these particles, and protons have a positive charge, let's call it +1, electrons a negative charge, and my experiment with a magnet could show that, and neutrons are neutral. So what we have is a situation where an atom is composed of these three types of particle. protons, electrons, and neutral neutrons. We find that atoms on their own are electrically neutral. They have no overall charge, and that means the number of electrons and the number of protons are the same as one another. They exactly balance. What we find is that the nucleus of an atom contains all the protons. It's very small and positively charged. We'll find that the characteristic of an atom of one element is the number of protons in the nucleus. For example, if we have, say, a hydrogen atom, that contains a single proton in the nucleus. We indicate that in the periodic table as an atomic number of 1. The atomic number in your periodic table is the one that's above the symbol of the atom, and it's above the symbol of the atom in this periodic table, and that indicates the number of protons in the nucleus. So something like carbon, atomic number 6, it has 6 protons in the nucleus. Uranium, atomic number 92, 92 protons in the nucleus, and so on. In a neutral atom, we have the same number of electrons as we have protons. So that in a neutral carbon atom, we have, for example, 6 electrons surrounding a nucleus containing 6 protons. But what I want to show you is really why we have neutrons. Imagine that to be a proton. That's a hydrogen atom, no problem with that. 1 electron somehow in an orbit around that will constitute a hydrogen atom. If I move to the next heaviest element, that is helium, atomic number is 2, 2 protons in the nucleus, and we have a problem. Protons are positively charged, and they will repel each other. So trying to squeeze 2 positive charges into one very small space is not going to work easily. If I go to lithium or even beryllium with 4 protons, try and make a nucleus containing just 4 protons, and it will blow apart. So that's not the whole answer. And this is really where neutrons come in. If we now include a few neutrons, indicated by the closed circles, in our nucleus, then we are able to get a unit that holds together. So it is only the hydrogen atom which can exist with no neutrons in the nucleus. All other elements must have some neutrons in the nucleus in order for the thing to hold together, for the nucleus to hold together. Now, what we find for the lighter elements, we generally have about the same number of neutrons as protons, or a little bit more. And as we go down the periodic table, as we get more protons, then we tend to have more than that number of neutrons present. So that an element like uranium, shall we say, typically would have 92 protons and, doing a quick calculation here, about 130 neutrons associated with the nucleus. The actual number of neutrons can vary a little bit, so that if we start off again with our hydrogen nucleus, most hydrogen atoms have no neutrons associated with it at all. But there is another form of hydrogen which has 1 neutron associated with it, and this is called an isotope of hydrogen. Isotopes are atoms of a particular element, defined by the number of protons, that have different number of neutrons in the nucleus. I'll write this on the board in a moment, and we find that with hydrogen it can have 1 neutron or 2 neutrons, or no neutrons at all. So there are 3 possible isotopes of hydrogen. And this balance of protons and neutrons is actually quite crucial for the stability of the nucleus. If it gets out of balance, then we have an unstable nucleus and we have radioactive decay. If we have, and that can occur if we have too few neutrons or too many neutrons for a particular number of protons. Now, I've given you a sort of fairly simplistic model of the nucleus. The more rigorous model says that the nuclear forces are a balance between electrostatic repulsion of the positive protons and what we call a strong nuclear force, which holds the whole thing together. And the strong nuclear force, providing that is greater than the electrostatic repulsion, we have a stable nucleus. If the converse is true, we have an unstable nucleus. Radioactive decay occurs and will continue to occur until we form an isotope that has a stable arrangement of protons and neutrons. And we find that the strong nuclear force actually occurs over really quite a small area. As a result of that, the nucleus has a maximum size in which it can be stable. Beyond that, it's unstable. And we find that maximum size occurs where we have around about 85 protons. So bismuth is the heaviest non-radioactive element in the periodic table. And all elements with an atomic number greater than that of bismuth at 83 are radioactive. Now, of the lighter elements, some may be radioactive and some are not necessarily radioactive. So, back to summarising a bit of this in terms of nomenclature for our atoms. We can describe an atom of any element in terms of its symbol. Let's take the symbol X, in terms of its mass number and its atomic number. And conventionally, we always put the atomic number as a subscript before the element symbol. We always put the mass number as a superscript before the element symbol. Let me call that A. And already you're seeing that if we want to specify mass number or atomic number, then we've got to be pretty careful where we put these things. Quick reminder from this morning's lecture that if we look at a formula like that of water, we use the space after the symbol and subscripted to indicate the relative numbers of those atoms within that molecule. So here we're looking at symbols before, and if I take something like hydrogen, the simplest atom of all is a hydrogen atom, and I might specify it like this. Atomic number 1 indicates that I have a nucleus with just one proton associated with it, and somewhere around that there will be an electron, so that the positive charge of the nucleus and the negative charge of the electrons exactly balance. Now, if I have the isotope of hydrogen that has a mass of 1, then we stop there, and that's the whole story. If, on the other hand, I have the isotope of hydrogen which has the mass 2, then that tells me this hydrogen contains one proton. By definition, that makes it a hydrogen atom, plus one neutron in the nucleus. And this is a stable isotope of hydrogen, and of a natural sample of hydrogen, about 1% of it is this heavier isotope of hydrogen. If you make water out of this heavier isotope of hydrogen, it's sometimes called heavy water. And indeed, if you make an ice cube of heavy water and put that ice cube in ordinary water, it sinks. So it is double the mass of hydrogen, a normal hydrogen atom. There is a third isotope of hydrogen, one in which there are 2 neutrons in the nucleus to the 1 proton. In this case, the nucleus has now become unstable, and this is actually a radioactive form of hydrogen. It's not naturally occurring, but we can make it synthetically. These are isotopes of hydrogen. Most elements have a range of isotopes that occur naturally. Carbon, for example, has a composition that's about 98% carbon-12, or 98.9% carbon-12, about 1.1% carbon-13, and then there's small traces of, for example, carbon-14. What this tells me is if I look at my periodic table, the atomic number of carbon is 6, so that in all cases I have 6 protons in the nucleus, but the mass number changes. The difference between these 2 numbers is the number of neutrons, and I can calculate that I either have 6 neutrons, 7 neutrons, or 8 neutrons in my nucleus of this carbon atom. Carbon-14 is radioactive, and that is used in what's called radiocarbon dating to age a material which is of archaeological age, hundreds or thousands of years old, but not really of geological age when we're looking at millions of years. So, isotopes of a particular element have the same number of protons. That defines the atoms to be that particular element, but different numbers of neutrons present. And what I want to focus on now is these electrons. And I think the first thing I want to do is actually show you a little bit of evidence, or show you an experiment which we will use to gather evidence for the position of electrons within a nucleus. And a lot of the experiments involve what we call atomic emission spectrum. And to start that, I want to show you something about the spectrum of white light. This is an experiment that Isaac Newton did in 1666. He actually did 2 experiments. In the first one, he took a pinhole of white light and he passed it through a prism, and when he did that, he saw the colours of the rainbow, the colours of the spectrum: red, orange, yellow, green, blue, indigo, violet, that you are familiar with. One of the things that made Newton a great scientist was his power of observation. And certainly when I look at that, and for many years when I looked at that, all I saw was the colours. What Newton saw was the colours, but he also observed that from a round hole, the spectrum you generate is a slight oblong shape. And that was quite unexpected. And as I say, it's powers of observation that make him into a great scientist. Now, in his second experiment, which I can't demonstrate, he took the colours of the spectrum and passed them through another prism and recombined them to give a dot of white light. And he made a number of interesting observations. He said, for example, that our eyes and our ears must work in a quite different way. So that when you see, say, a dot of white light, his first experiment showed that it was actually made up of the colours of the spectrum. However, when we perceive it, we see just white. We don't think, oh yes, that's green, blue, indigo, violet, etc., all mixed together. On the other hand, if you hear a musical chord, the ear can pick up the fact that it's a combination of notes. So ears and eyes work in a different way. He also, it is suggested, chose the 7 colours of the spectrum red, orange, yellow, green, blue, indigo, violet, chose those 7 colours of the spectrum to be somehow, and if you excuse the pun, in harmony with the Western musical scale. Because the colour of the blue, indigo, violet, it's a little bit of a subjective call there. What I've shown you, however, is what we call a continuous spectrum, where white light is split evenly into the whole colours of the rainbow. A lot of the evidence, early evidence for electron orbits, comes from the atomic emission spectrum of atoms. And in this case, we find that if we put energy into an atom, we can get some of that energy out again in terms of light. The wavelength of light is related to energy levels within the atom. And moreover, the wavelength of light is specific to the particular atom or element that we have. I want to just show you some of this. If I light my Bunsen. Don't know whether you've ever thought about what a flame is. Quite magical and mystical, but I'd say that a flame is just a chemical reaction that happens to give out heat as well as light. And in general, it's the heat that we're interested in. So, I've got my flame, I've got an energy source, and what I'm going to do is actually spray into that energy source some different chemicals. And if I spray into the flame barium, I get a slight greenish colour. I'll dim the lights one more stage. And we find that each element has a characteristic colour associated with it. Those red flecks indicate lithium is present. Potassium looks yellow. That's a bit of a false one. Underneath that there's a little bit of a purplish colour. I'll say more about that in one moment. Strontium, these are the colours of fireworks, of course. Strontium, a nice crimson yellow colour. Copper, my personal favourite, is this kind of yellowy green colour. Sodium, as another and final example of this, anyone that has a gas stove and uses salt in cooking, you see the veggie water boil over and you get this yellow colour characteristic of sodium. And it's a very intense emission. If you see one of the orange street lights light up, they are based on sodium. And it's actually quite an efficient way of converting power in the form of electricity to light. The phenomena that you see in a street light is exactly the same as this. We are moving electrons around from one energy level to another. When a street light, a sodium street light, first turns on, it's not yellow, but it's actually a purple colour. So have a look at that sometime when winter comes, and that purple colour is potassium. In the periodic table, sodium and potassium are close to one another. They're above each other in the periodic table. Now, one of the trends that we see in the periodic table is that as you go from, for example, sodium to potassium, you're going to a metal that has a lower melting point, is volatilized, made into the gas phase more easily. When a street light is first switched on, there's a little bit of potassium in the atmosphere at room temperature within the light bulb. That will start to glow a purple colour. That will allow the electrical current to flow within the light bulb, which will then heat up a little bit, which will evaporate sodium, which is also there. As soon as we have sodium in the atmosphere, then that will start to get energized by the electricity, give out light of its characteristic wavelength, and that happens to be yellow and very much more intense than the potassium. Potassium doesn't go away, it's just the intensity of the colour is swamped by that of sodium. I mentioned this morning the element helium. discovered first on the Sun, and it was discovered by its atomic emission spectrum, as we call it. Now, there's a number of periodic tables that you can find on the web. And one of the periodic tables, and the URL for this is the bottom of page 3, looks like this. And this actually gives the atomic emission spectrum of all the elements. If you click on them in the periodic table, you find you get a series of lines. So this is the atomic emission spectrum of hydrogen. When the balloons exploded this morning, you saw an orangish flame. That was a combination then of an emission of light in the red region of the spectrum and a little bit in the blue region of the spectrum. If I look at another element, say carbon, I have a different set of lines. The atomic emission spectrum differs from the spectrum that Newton saw in that we have discrete colours associated with each element. And different elements have a different set of lines. Every element has associated with it, if you like, a different colour in its atomic emission spectrum. I mentioned cesium this morning. I mentioned rubidium this morning. From the Latin rubidus for red, it got its name because of this emission in the red region, which was at a wavelength that only rubidium showed and no other element showed. And some of the elements are extraordinarily complex in their atomic emission spectrum. Okay, what does all this mean? Well, our interpretation of the atomic emission spectrum of an element is that what we're observing is movement of electrons within the outer part of an atom. We have, remember, our model of the atom where we've got a small positive core containing the protons and the neutrons. That's where all the mass is. And around this, and we'll see that they occur in certain orbits, are the electrons. When we give an atom some energy, we allow an electron from an inner orbit to move to an outer orbit, and the atom absorbs that energy. But that's a little bit unstable. The electron wants to be as close to the nucleus as possible because electrons are negative, nuclei are positive, and there's an attraction there. So the electron returns to the orbit closer to the nucleus, and in so doing gives out light of a particular wavelength. And it might do this in a number of stages. If it does it all at once, we'll get wavelength, a unique wavelength. If, for example, the electron moves to, let me do this in a different colour, that might help. If an electron moves to a different orbit, I will also get light given out, but it's going to be of a different wavelength. So we end up with a series of lines associated with light emitted by the atom when an electron moves from one orbit to another. The wavelength of those lines in the spectrum is directly related to the energy difference between the electron orbits. No two elements have the same series of filled and unfilled electron orbits, have the same number of electrons associated with them. So each element has a unique set of lines associated with it. Well, let's see how this works in practice and how we can relate it to the periodic table. And taking the simplest of the elements, hydrogen, it has one proton in the nucleus, atomic number 1, hence 1 electron. And I'm going to represent that electron as a cross in an orbit. If I look at the next most complicated element, helium, atomic number 2, 2 protons in the nucleus, it also has 2 neutrons and has 2 electrons. And I'm going to put them both there in an orbit. Now, these electron orbits are rather like onion skins in that the closer to the nucleus they are, the smaller they are. The further out they are, the bigger they are. Electrons are negatively charged and they repel each other. So I can't cram too many of them in one space. The next element we look at, lithium, atomic number 3, that means 3 protons, and hence 3 electrons. And what I find is that this innermost orbit is filled. The 3rd electron in lithium needs to go to a 2nd orbit. There's not enough room in the 1st orbit. And if we walk across the periodic table, the next element is beryllium. Atomic number is 1 more than that of lithium. It consequently has 1 more electron in the uncharged atom, total of 4 electrons, filling up the orbits. 2 go in the innermost orbit, the remaining 2 in the next orbit. What's next? Boron. 1 more electron. Carbon is next. Atomic number is 6 protons in the nucleus. Six electrons associated with it, and they are in an electron configuration of 2 electrons in the innermost shell or orbit and another 4 beyond that. This 2nd orbit is quite a bit larger than the innermost one, so it can contain many more than 2 electrons. And as we cross the periodic table, nitrogen is next. I'm going to start pairing up the electrons so it's easier to keep count of them. I've got a 2-5 arrangement. Oxygen. I've got a 2-6 arrangement. Fluorine's next. Fluorine is actually quite unusual in that it is one of the elements that has very, very few isotopes in the naturally occurring state. It has an atomic number of 9 protons, has 10 neutrons in almost all cases, and it has 9 electrons. 2, 4, 6, 8, 9 electrons. And then beyond that, it's getting a little bit crushed here. I have neon. And following the periodic table, I'm going to start a new row when I get to the next element, atomic number 11, which is sodium. And what I find is that I have now filled the 2nd electron shell. So the 2nd electron shell can contain a maximum of 8 electrons in it. And that's represented by the gas neon. Sodium. And I will stop this in just a moment. We have 11 electrons associated with sodium. And the best way to distribute them is packing them into the orbits closest to the nucleus. I can only fit 2 in the first one. I can fit 8 in the next one. And now the 11th electron goes into the 3rd orbit. And if I look at, let's say, one more element, magnesium, I hope you can start to see that there is a bit of a pattern here. And the bit of the pattern enables us to understand the shape of the periodic table. And what we find is that the periodic table is the shape it is because it reflects the electron configuration of the atoms. In all cases, I'm talking about what we call the ground state electron configuration. Of course, any element, let's take hydrogen, it has a whole lot of electron orbits, but it's only got one electron. The most stable place for that electron is here. I need to put in energy and it can be moved to any of these others, but then will fall back ultimately to the most stable situation. So in all these cases there are a whole lot of empty electron orbits which I haven't bothered to put on my diagram. But how does this reflect the periodic table? Hydrogen and helium, the electrons occupy the first shell. They're the elements in the first row of the periodic table. And we call a row a period. In the case of the elements lithium to neon, they have electrons in the first two shells, and they're in the second period of the periodic table. Sodium and magnesium, electrons in three shells, they're in the third period of the periodic table. If I take an element at random, let's say this one, Sn stands for tin. I see that it's in the fifth row of the periodic table, and I can instantly say, okay, it has 5 electron shells. 4 of them will be completely filled, and the fifth one will be partially filled. So the coordinates of an element in the periodic table tells us directly the electron configuration. And when we do bonding, we'll find that's really important, because if you think of two atoms colliding, what's going to meet first? It's going to be the outer electron shell. So if we understand something about those outer electron shells, we can predict something about the reactivity of the material. Okay, what other trends can we see? Lithium and sodium appear to come below one another in the electron configuration, and we find that all elements in that first column, and the correct name for a column of elements is called a group, all of the elements in that group have one electron in the outermost shell. All elements in group 2 have 2 electrons in the outermost shell. All elements in group 14 below carbon will have 4 electrons in the outermost shell, and the elements below neon will all have 8 electrons in the outermost shell, so that we can take our cue from the second row elements as to what the electron configuration of all the other elements below it are. If reactivity is going to be associated with the outermost electron configuration of an atom, then it's probably no surprise that any atom that has, say, an electron configuration with just a single electron on the outside will react in a similar way. Other atoms which have 5 electrons on the outside, such as nitrogen, phosphorus, and heavier elements, will react in a similar way. I can, at random, select an element, let's say bromine, and say, okay, position in the periodic table tells me it's in period 4, the 4th row. That means there are 4 electron shells, 3 of which are filled, and the 4th one is going to be partially filled. How many electrons are going to be in the 4th one? Well, it's going to be the same number of electrons as there are around fluorine. And if I count left to right, fluorine is 7 notches, 7 squares along from the start of that row. So bromine's going to have an electron configuration in which there are 7 electrons in that outer 4th shell. If I look at indium, I don't need to count up to 49, which is the number of electrons indium would have. I can instantly say the interesting bit is going to be the 5th shell, because that's the outermost shell that will be partially filled. It will have 3 electrons in it, because that's the number of electrons that boron has in its outermost shell. So the answer is all in the periodic table as far as the electron configuration goes. What we observe in the periodic table is the fact that the elements on the extreme right-hand side, as we portray them, all have a completed electron shell. If I was to draw, for example, argon, third row, 3 shells, and in the most stable situation I'm going to have all electrons in the shells closest to the nucleus. I can get them, and in the case of argon it's going to be a 2-8-8 arrangement of electrons. If I were to look at the next atom higher in atomic number, that's potassium, atomic number 19, and I have to start a new electron shell in order to accommodate that 19th electron. So, electron shells. Smallest one, closest to the nucleus, can hold the fewest electrons. As the atoms get bigger, the orbits get, or the orbits that are used get further out, they can contain more electrons. Also notice that it is the elements on the extreme right-hand side that are the only ones in nature that occur on their own as monatomic gases. What do I mean by that? This morning when we were talking about elements and compounds, I said there was approximately 90 naturally occurring elements, another 30 that we've made, but there are currently 15 million compounds that we've identified and characterized. Compounds are very much more numerous than elements. They're more stable than elements. We'll see why tomorrow. But what I find is that of the elements in group 18 of the periodic table, and including helium, neon, argon, working down the group, krypton, xenon, radon, they all occur as nature uncombined. They don't form compounds. They occur as monatomic gases, that is, single atoms. Other elements like oxygen and nitrogen, well, they occur in nature, but they occur as diatomic gases. And also, in the most cases, they occur as compounds. There is something about this electron configuration which makes it special. We find that a completed electron shell is a particularly stable arrangement of electrons. And I can predict how I might be able to complete that electron shell for some of these other elements. The last topic I want to talk about is the formation of ions, and then I'll summarize things. And an ion is a charged atom. Well, think for a moment how we might be able to get a charged atom. I can't do anything about the number of protons in the nucleus because they are buried in the center of the atom, are inaccessible under normal circumstances, and they're fixed. Moreover, they fix the type of element that atom is. But what I can do is something with the electrons surrounding the nucleus. They're the outermost part of the atom, and I might be able to remove electrons, and we've seen experiments where we can observe electrons on their own. I might even be able to add electrons to materials. If I take something like, say, sodium, the electron configuration of the atom looks like a 2-8-1 type of configuration. If by some means I can remove an electron, I will end up with a species in which I have stripped the electron configuration back to 10 electrons. I've removed that outermost electrons, and now what I see is that I've ended up with a completed electron shell. But what's happened to the charge? Well, sodium still has the same atomic number because that's what makes it sodium. It's 11 protons in the nucleus. But now I've a total of 10 electrons, and overall I've got an imbalance of charge. And that is what an ion is. I can indicate the charge by the top right corner. That's the only position left we have, and conventionally charge is put as a superscript after the atom it represents. And I would predict that sodium as an Na plus ion is going to be stable because it has the same electron configuration as neon, and I know that is a stable atom. If I remove another electron, then I break into this second shell, and I'd once again go back to a situation where I have an incomplete electron shell, and that's not going to be so favourable. If I took perhaps magnesium, you can see perhaps what's going to happen. Third row, 3 shells, second group, 2 electrons in the outermost shell. If by some means I remove 2 electrons, I strip magnesium back to the same electron configuration as neon. I've removed 2 electrons, so I've now got an imbalance of 2, and I have a magnesium 2 plus ion. And if I have a positively charged ion, we actually call those cations. So positively charged ions are cations. Well, I could do this for any of the elements in theory, but of course we have a little bit of a problem. If I remove an electron from an uncharged atom, that works okay. If I remove a second electron, I'm now trying to remove a negatively charged particle from something that's already positively charged, and that takes more energy. If I look at, say, carbon, to strip that back to a completed electron orbit, I'd have to remove 4 electrons, and that's really hard work and tends not to happen. But what I might be able to do, and let me take, say, fluorine as an example here. Instead of removing electrons, I could add electrons, and in the case of fluorine and all the elements in that group 17, if I add an electron, it can now fill the orbit that's partially filled and end up with an electron configuration that is the same as that of the nearest noble gas, that of neon. Well, I've now got more electrons than protons, and I've got a ion which has a negative charge. And negatively charged ions we call anions. Now, for reasons that I don't quite understand, when we produce a negatively charged ion from an atom, we actually change the name a little bit. And instead of calling this a fluorine anion, we call it a fluoride anion with an IDE at the end. And one final example of this series, if we take, say, oxygen and look at the electron configuration, specifically the electron configuration in the outermost shell or orbit, well, I find there are two gaps. And I could imagine by some mechanism I can add two electrons, and in so doing I will end up with an O2 minus anion, or an oxide anion, but I'll have a completed electron shell, and so I'd predict this to be stable. These ions, we say, are isoelectronic with the noble gas closest to it, and in all cases that is neon. Isoelectronic means same number of electrons. If we can get to an electron configuration that is isoelectronic with a noble gas, then that is likely to be a stable arrangement.